Welcome to today's explainer. Today, we're looking up, like way, way up. You know, when we think about the universe today, we picture this endless, expanding void, right? Billions of galaxies, each packed with billions of stars. Honestly, it's a scale so massive it kind of breaks your brain to think about. But here's the crazy thing. Just over a century ago, humanity's view of the cosmos was incredibly small. We were basically sitting in a giant, pitch-black room with a tiny little flashlight, completely oblivious to the vastness right in front of us. So how did we finally flip the lights on? How did we actually figure out just how massive the universe truly is? Well, the answer doesn't start with some giant famous telescope, but rather with the quiet, absolutely meticulous work of a single brilliant researcher. Okay, let's dive into this. To really appreciate this solution, we gotta understand the massive brick wall astronomers hit back then. Before the 20th century, the biggest problem wasn't seeing the stars. It was figuring out where they actually were. I mean, think about it. If you look up at the night sky and see a super bright star, you can't really tell if it's just a small star hanging out relatively close to Earth or a massive, blindingly bright star that's millions of light years away. It's a visual trick. Because of this, astronomers had zero reliable ways to measure distances beyond, say, a few hundred light years. They were totally stuck. To them, the Milky Way basically was the entire universe, and everything was just kind of right there. We needed a cosmic ruler. We essentially needed a way to measure the infinite. Section 1. The Harvard Computers, also historically known as Pickering's Harem. So back in the late 19th century, the Harvard Observatory, which was, as you might guess, heavily male-dominated, hired a group of women to do the tedious, exhausting work of analyzing a massive flood of new star data coming in on glass photographic plates. And one of these brilliant researchers was a woman named Henrietta Swan Leavitt. She was soft-spoken, incredibly hardworking, and doing all of this while dealing with a severe personal challenge, a progressive hearing loss that would eventually leave her nearly deaf. But man, her focus was just absolute. At the observatory, Leavitt got assigned to study a very specific astronomical phenomenon called variable stars. These are stars whose brightness isn't constant. Instead, their light actually ebbs and flows. They dim and brighten over these very predictable, regular cycles. It's kind of like a giant lighthouse slowly rotating in the deep, dark ocean of space. And that's exactly what Leavitt was tasked with tracking. Which brings us to Section 2, the breakthrough, the Magellanic Clouds. Now, Leavitt developed this painstaking, incredibly meticulous method to track these stars. She'd take multiple glass photographic plates of the exact same patch of sky, taken at different times, right? And she would literally just overlay them. By doing this, she could spot the absolutely tiniest changes in starlight. Using this technique, she managed to catalog a staggering 1,777 variable stars, located specifically in the Magellanic Clouds, which, spoiler alert, we now know are neighboring galaxies. But just think about the sheer volume of work here. Finding, verifying, and tracking nearly 2,000 individually pulsating stars by manually comparing glass plates with the naked eye. Her attention to detail was just off the charts. But she wasn't just collecting data for fun. She was zeroing in on a specific subset of these pulsators called Cepheid variables. And looking at this massive mountain of data, she noticed something genuinely extraordinary. And this brilliantly illustrates the absolute stroke of genius in her work. Leavitt realized something crucial about the stars she was looking at in the small Magellanic Cloud. Since they were all clustered together in that specific cloud, for all intents and purposes, they were essentially the exact same distance from Earth. So, why is that such a big deal? Well, because it completely eliminates the distance variable. It meant that how bright a star appeared to be from Earth was a direct one-to-one reflection of how bright that star truly was intrinsically. She didn't have to guess anymore if a bright star was just closer to us. She knew for an absolute fact that if one star looked brighter than another in that cloud, it actually truly was brighter. That realization right there led to her defining publication. In 1912, Leavitt published a landmark paper that totally changed the game. By focusing on these Cepheid variables, she laid down a strict, undeniable mathematical rule. She basically proved that there was a direct link between a Cepheid star's true brightness and how fast it pulsed. Specifically, the brighter a Cepheid variable star was intrinsically, the longer its pulsation period took. So a dim star might pulse every few days, but a massive, blindingly bright star, that one would take weeks to complete its cycle of dimming and brightening. It was a perfect, completely predictable cosmic rhythm. Moving on to Section 3, the Cosmic Yardstick, Leavitt's Law. This simple but deeply profound mathematical rule became known as the period luminosity relationship, or, as we rightly call it today, Leavitt's law. Without even setting out to do so, Henrietta Swan Leavitt had inadvertently handed humanity a literal cosmic yardstick. So the crucial point is, how does this actually work in practice? Well, it's this beautiful three-step process. Step 1. An astronomer spots the Cepheid star somewhere in the night sky, and all they have to do is sit back and time its pulsation period. Step 2. They use Leavitt's law, and that time instantly tells them the star's true intrinsic brightness. And Step 3. By comparing that true brightness to how dim the star actually looks from down here on Earth, they can calculate its exact distance using the inverse square law. It's exactly like knowing for a fact how bright a 100-watt light bulb is, and then just measuring how dim it looks to figure out exactly how many miles down the road someone is holding it. It's brilliant. Which brings us to Section 4, an expanding universe, the tragic but monumental legacy. Now, this is where our explainer takes a bit of a bittersweet turn. Let's walk through this timeline together. As much as we celebrate this monumental scientific contribution Leavitt made, we really have to contrast it with her tragic personal reality. So her landmark paper comes out in 1912. But just 9 years later, in 1921, Leavitt tragically died of cancer at the age of only 53. She passed away entirely unaware of the massive seismic shift her work was about to trigger in the scientific community. And the bitter irony here is just, it's profound. In 1925, a Swedish mathematician realized the sheer magnitude of what she had discovered and actually attempted to nominate her for a Nobel Prize. He was completely unaware that she had already been dead for 4 years. And it was just shortly after her death that a guy you might have heard of, Edwin Hubble, stepped onto the stage to pick up her yardstick. Now, what's really interesting about this slide is how all the pieces of the cosmic puzzle finally snapped together. Astronomer Edwin Hubble took Leavitt's law and pointed it directly at the Andromeda Nebula. Using her yardstick, he measured the distance and proved definitively, once and for all, that Andromeda wasn't just some dusty cloud of gas inside our own galaxy. No, it was an entirely separate galaxy far, far outside the Milky Way. Literally overnight, the known universe became vastly larger than anyone had ever imagined. But Hubble didn't stop there. He combined Leavitt's distance measurements with galactic redshifts, which are basically changes in the light spectrum that tell us if something is moving. By putting her distances together with those shifts, Hubble proved that these distant galaxies are actually flying away from us. He established that the universe itself is actively expanding. The entire scale of what we know today, the billions of galaxies racing outward in this massive expanding universe, it all comes back to her. As the source text so beautifully summarizes, the man who unlocked the scale of the cosmos stood squarely on the shoulders of a quiet researcher who spent her life mapping the blink of distant stars from a freezing attic office in Cambridge. I want you to really let that profound contrast sink in for a second. The greatest, most massive physical reality we can even comprehend, the expanding universe, was discovered because of the marginalized, tedious work done by a nearly deaf woman in a freezing attic office who history almost forgot. Which leaves us with this final, lingering thought for today's explainer. Henrietta Swan Leavitt handed us the literal yardstick to measure the infinite, and yet she labored largely in the background of a male-dominated field, totally uncelebrated in her own time. It really makes you wonder, doesn't it? How many other foundational discoveries, the very building blocks of our modern understanding of the world, were made by people that history just casually overlooked? Thank you so much for joining me today to explore this. Keep asking questions, keep looking closely at the data, and most importantly, keep questioning the history of science. I'll catch you in the next one.